This video is sponsored by Diamondback and also promotes like a dozen companies. Trust me, it's worth it. I'm on a mission to test out every single 3D filament ever made, and we have made it to the cutting edge. I've already shown almost every filament you can buy. Today, we will feature the ones you can't. From shape memory polymer to jacketed fiber core nylon to biocompatible human bone, these next-gen polymers let you 3D print the otherwise impossible. This one blocks radio waves going in and out. This wireless power circuit is fully printed. We got filaments to block X-rays, gamma rays, and neutron radiation. It's been over a year since the last installment, and here's why. I'm not even supposed to know some of these filaments exist. Some are exclusively B2B, others are made to order, and even though you could buy the rest, you would need an expense account to pay for them. Ladies, gentlemen, and cyborgs, snug your ties, shine your shoes, and latch your briefcases, because you're about to see like $10,000 of filament made by companies for companies. My name is Zach Friedman of Voidstar Lab Incorporated, and these are my business filaments. Quick disclaimer before we dive in. In order to get my hands on some of these filaments and the equipment to actually print them, I had to cut deals with over a dozen suppliers. No cash changed hands, I am not under any contracts, and apart from preserving trade secrets, none of these firms can demand any changes to the script. However, I am obligated to do things like mention talking points, talk about the companies, show some logos, etc. This gave me privileged access to dozens of exotic filaments that have never been seen on YouTube. But it also means I have to do a bit more shilling than usual, and I promise to reward your patience as best I can. Patreon support was also crucial. Not everyone wanted to play ball, so I had to spend thousands of dollars sourcing and importing weird filaments from around the world. Finally, I'd like to thank today's sponsor, Diamondback, for making all this possible. We're about to print ceramic composite that's harder than ruby, heat-sinking thermal compound filament, and gloopy literal glue. And we're going to do it almost entirely on Diamondback nozzles. I don't believe I could have actually pulled off many of these wacky filaments without their polycrystalline diamond 3D printer nozzles. They just bought a plug, not an endorsement, but they're getting one anyways because I love this product. It is the perfect 3D printer nozzle, and the difference is immediately noticeable. Diamond isn't only the hardest material, it's also a record-breaking thermal conductor, and its low coefficient of friction means stuff hates sticking to it. This means Diamondback nozzles give you peak performance with almost any filament at almost any temperature on almost any printer. They even make official all-in-one hot ends for bamboo printers, and they even introduced those Prusa neck extruder awkwardly long nozzles on a stick things. I've installed a Diamondback on almost every printer I own. Some of them have been running for years. Abrasive filaments, caustic filaments, $8 a kilo sweet deals from AliExpress. These tips still look brand new, and I've never had to cold pull a clog. But they still improve the design. Diamondback nozzles are now made of nickel-plated copper that melts more filament per second, and they even rounded off the diamond tip to make it that less likely to collect carbonized crud. Diamondback's products are fully American-made and absolutely gorgeous if you're into those kinds of things. Click the link in the description to give your printer one of the easiest, most effective upgrades you can possibly make. And speaking of aftermarket parts, if your printers are your projects, you might recognize our first brand, IGUS. This German polymer manufacturer is best known for solid linear bearings that slide in total silence and never need grease. But IGUS products go on your build plate too, with this line of unique filaments that feature their patented tribo technology. Tribology is the science of rubbing shit together. These filaments cut friction and reduce wear, no lubricants required. If you saw my Advanced Filaments episode, you already saw an IGUS filament, Tribo Plus. This was one of the worst, most obnoxious bastards of a filament I have ever featured. Well, one of their reps reached out with two key pieces of missing information. First, they had BuildTak develop a special print surface specifically to stick down filament designed not to stick to anything. Second, Tribo Plus had already been discontinued when I shot that episode. These are its successors. First, we'll start with IGUS's entry-level iGlide and I-151. These PTG composites are easier to print than the regular kind, but they slide about 25% more smoothly thanks to solid lubricants mixed right into the polymer. They also have phenomenal abrasion resistance that even beats nylon. I have actually used these filaments in a few projects on this channel, like the sabos and shell casings for my chocolate Nerf darts. iGlide really does slide smoothly, even against sticky, melting junk food. And that's actually an intended use case. No, not shooting chocolate out of a Nerf gun. The only physical difference between the two is the color. I-151 is blue because food, drinks, and pharmaceuticals generally aren't. This is meant to make production lines for consumer packaged goods. If a piece of the machinery snaps off and gets mixed into the product, an optical inspection system can easily spot that distinct blue color for a QA tech to pick out. You'll actually see a number of filaments today with special features meant specifically for industrial automation. It's one of the more common reasons big companies even use 3D printing. Then there's IGUMID P150. This is a tribo polymer like iGlide I150, except reinforced with carbon fibers. Everyone knows carbon fibers are abrasive and they'll sand down your nozzle, but your prints will also sand down whatever they're sliding against. That makes this filament unique in a very useful way. It lets the carbon fibers stiffen and strengthen your parts without sanding down whatever those parts are touching. But this stuff really shines in a multi-material machine. The rigid P150 can reinforce the softer I150 so you can get both ends of the material science ice cream cone. Rugged, rigid mechanical parts with long-lasting self-lubricating surfaces. Next is IGUS I180, the closest comparison to that old Tribo Plus. This is one of the most rugged ABS filaments I have ever tested. A full-on assault with sandpaper barely left a mark. ABS is normally prone to warping, but IGUS additives make it far more friendly, especially on that special build tack surface. This filament is specifically meant as an upgrade for nylon, especially when you have to print long, thin bar shapes. Nylon hates long, thin bar shapes. Oh man, imagine if a bar actually was made of this IGUS filament. Your sarsaparilla would go into orbit. Here's our final IGUS filament. IGUMID P190. This ditches the tribological tomfoolery for straight-up stiffness. Originally meant to reinforce another tribo filament, I190, P190 is one of the most rigid filaments I have ever seen, and while IGUS hasn't disclosed exactly what's in it, the heat resistance, brute strength, and oddly low density imply it's some kind of carbon fiber polycarbonate. Whatever it is, it's perfect for its primary market, custom robotics. It's also our first filament that can't be purchased off the shelf. IGUS exclusively sells P190 directly business to business, as in have your procurement department submit a declaration of intent. Let's shift to a brand you might have seen, but have almost certainly never actually seen. Addnorth. This Swedish manufacturer exclusively distributes in Europe. There's only one place you'll see that name in America, at the top of Prusa Slicer's filament list. And I did, so I reached out and somehow ended up hornswoggling those Swedes into sending their flashiest spools straight from their factory. Addnorth has a full range of funky filaments, including the handsome TPU Pro Matte, the fully recycled dripped out Adnite, and Textura Flare, soft touch PLA with a subtle classy sparkle. But their specialty filaments are on another level. We'll start with Coltron G1, a graphene-filled PVDF that could be the most sci-fi thermoplastic ever created. Graphene is a pure carbon allotrope like diamond, except its atoms form nanoscale sheets that grant it some silly-sounding statistics. Graphene is technically the thinnest, strongest known material, and it's one of the best conductors of both heat and electricity. It also happens to be one of the blackest substances ever developed. But you don't see very many graphene filaments because you can't just dump the stuff into the hopper like carbon fiber. The nanoflakes like to clump together, which just neutralizes their properties. But the Swedish materials science firm Graphimatech figured out how to prevent this, how to disperse graphene evenly in a polymer. And Addnorth is the only company to license their tech for 3D printing. So accept no substitutes. Coltron G1 is the only graphene filament that gives you the whole nano hog. Here come the numbers. The electrical resistance of Addnorth Coltron is only 2 ohms per centimeter, which is low enough to print circuits and sensors. Its thermal resistance is barely half a watt per Kelvin meter, about the same as those white packets of thermal grease. And this filament has one of the lowest coefficients of friction bar none, because the plastic itself is a low friction superpolymer. In my cursed filaments episode, I showed off pure PVDF, or polyvinylidene fluoride. It's a chemical cousin of Teflon with low friction, high strength, and extreme resistance to heat, chemicals, and radiation. It can also release terrifyingly toxic gases if it gets too hot, but I'll admit I overplayed the risks last episode. Something has to really go wrong for hydrofluoric acid to start flooding your 3D printer workshop. PVDF has the lowest coefficient of friction of all pure plastic filaments I'm aware of, while graphene has one of the lowest coefficients of friction of all materials, period. This means Coltron is some super slippery stuff. But don't worry, IGUS, your stuff is far from obsolete. The nanoglitter also sabotages PVDF's layer bonds, making this one of the weaker filaments I've ever tested. Oh yeah, it's also a casual €800 per kilo. But from a commercial standpoint, if you need it, you need it. Graphene's unique properties, combined with PVDF's kitchen sink of superpowers, make Coltron G1 something of a silver bullet for printing the otherwise unprintable. It's also not Addnorth's most expensive filament. It's not even a top 5 for this episode. This one is Adbor N25. 75% nylon plus 25% boron carbide equals one of the most effective radiation shielding compounds in convenient printable form. B4C is not a JoJo reference, it's a ceramic, most famously used to make level 4 ballistic plates the highest rating of body armor. Here, boron carbide provides a different kind of protection. Adbor N25 is a neutron capturing filament. If a strong independent neutron happens to T-bone another atom right in the nucleus, it can actually get stuck. This turns what was previously a very stable atom into a radionuclide that will almost certainly eventually decay. But some atoms absorb free neutrons more easily. Some of those can eat a bunch of them before they finally fall apart. Some of those decay into safer byproducts than others. Boron lives dead center in that Venn diagram, and boron carbide is a great way to park it in a 3D filament. You can 3D print like control rods and shit. You shouldn't, but you could. To be absolutely clear, you should never do any kind of project that requires this level of radiation shielding, even if you too have a chunk of uranium ore you bought from Amazon. America! The freedom to do the dumbest shit you could possibly imagine. You'd be better served by something like Josef Prusa's Tungsten Prusament PTG by Josef Prusa Research. Later. Get out of here, Josef Prusa, winking. One final note, Adbor N25 is the most abrasive filament in existence. Fiberglass is a notoriously abrasive nozzle killer, and that's a 6 on the Mohs hardness scale. Boron carbide is a 9.5. Forget hardened steel, this will eventually blow out a ruby nozzle. Not that you could ever afford to do so, this filament is €1,500 per kilo. If you're curious, it won't kill a diamondback nozzle because diamond is a perfect 10. If you're very curious, you can actually get diamond filament. This is Carbodeon Micro Diamond PLA, and it features real nanoscopic diamond particles. But this stuff won't even hurt a brass nozzle. Finely ground diamond crumbles into chubby little polyhedra, not edgy shards, so they can't really scrape up the inside of a nozzle. While it's made with industrial diamond grit, it's actually meant for a hobbyist purpose, making speed benchies. Diamond's extreme thermal conductivity makes this melt faster so you can print faster. Don't know why they made it PLA though, would have made more sense to do ASA. It's not a business filament unless, is anyone being sponsored to make speed benchies? Is it like Formula 1? Any people out there with like printers bombarded with stickers, like running off really fast boats? Micro diamond filament doesn't really conduct heat once it's printed, but like it wasn't really designed to. Our next filaments were. These are Ice 9 TPU and Ice 9 nylon from TCPoly, named after an apocalyptic substance from a Kurt Vonnegut novel. This filament is much less catastrophically dangerous, unless you're a nozzle smaller than 0.6 millimeters, because this stuff jams like Rick Moranis' radar. TCPoly recommends an 0.8 millimeter nozzle and 0.6 millimeter layers, the most cake frosting default setting I have ever seen. Why so thick? There's so many C's in there, it adds a line break. Ice 9's datasheet mentions 2 mysterious mix-ins, proprietary filler A and proprietary filler B. And they're there in such high quantities, there could be more Reese's Pieces than Froyo. There is so much shit in this shit. Ice 9's thermal conductivity is nominally 2 to 6 watts per meter Kelvin, as high as some metals and, as it happens, ice. Depending on the specifics, heat will spread through Ice 9 filaments 8 to 100 times faster than it would through pure plastic. My only gripe is the TPU in particular. It just has so much crud in it, its layers flake apart. We've seen this issue before. One of the cursedest filaments in the Cursed Filaments episode was carbon fiber TPU from Smart Materials 3D. They split the difference between stiff and supple by packing this flex filament with particles, and the results were simultaneously weak and still kind of flexible. Well, those Spanish Científicos Locos redeemed themselves with TPU Hardness Plus. This stuff is stiff, like really stiff. But it's not from fiber fillers. It's better living through chemistry, and it makes all the difference. Thermoplastic polyurethane is a flexible polymer, but at 83 Shore D Hardness Plus is stiffer than most nylons and ABS. When you don't saturate it with shmoo, TPU has the strongest layer bonds of any polymer, which makes it practically indestructible. It also has really good heat resistance and can handle some UV rays. But all these properties are usually drowned out by the fact that it's flexible. Well, Hardness Plus lets you harness all those superpowers without f***ing with the floppiness. TPU Hardness Plus is expensive, it is a bit harder to print, and it gets waterlogged in like hours. But all that is fine. If you're, for instance, a biomedical engineer, there are not many filaments that are both invulnerable and capable of being UV sterilized. I want to take a little tangent to feature another Smart Materials material that smartly materializes today's theme but in reverse. This is Olive PLA, very much a hobbyist filament, but it's made with industrial byproducts. This biodegradable PLA is not named for its olive drab color, it's named for the actual olives, like it's stuffed with ground up olive bones. Look, it says olive bones in the product page and I'm sticking to it. Wasted olive bones are actually a relevant local issue. Spain is the Drupaceous evergreen's top producer and one of the world's most prolific consumers. Last year alone, the country loaded its landfills with over 3 metric tons of olive bones and other olive carcasses. Putting pits in PLA actually makes a lot of sense. The olive oil production process pulverizes them, so unlike wood filament, you don't get little flakes of sawdust clogging your nozzle. Unfortunately, this does not make your print smell like a dirty martini. Maybe one day I can get a little vermouth filament, get some gin filament, run it through that mosaic to mix them all together. As the Goldblum said, a life finds a way. We just lost all our patrons, all of them. Next up is Phaetus. Phaetus? Whatever. This Chinese firm's high-end, dare I say luxurious printer parts are well known by serious hobbyists. Their Rapido and Dragon hot ends are the de facto standard for Vorons. Well, at last year's Rocky Mountain Rep Fest, one of their reps slipped me some samples of their newly released industrial materials, and I knew right away this was some wild-ass filament. We'll start with Phaetus's AE Force PAHT, a high-temperature nylon that's just built different. Most nylon filaments are PA6 or PA12, PA being short for polyamide. But this stuff is probably polythalamide, stiffer, stronger, and more stable in higher heat and harsher chemicals. While it's meant to run on a commercial Fab Lab's high-powered printers, PPA is trivial compared to similar superpolymers like PEEK. I'm demonstrating this on the Pantheon HS3, a fancy pants high-spec machine meant to print industrial strength parts all day in carbon fiber PET and polyamide. This is exactly the kind of printer filaments like this are meant to print on. Yeah. PPA is somewhat rare, but it's by no means proprietary. The next filaments are very much both. Phaetus's AE Coating Next PA jacketed nylon composites. These pack PAHT with a generous 25% of carbon or fiberglass and then wrap that in a pure polymer skin. The result is a half composite filament with a bullseye cross-section. And since a nozzle needs laminar flow to print properly, there's no turbulence to mix them together. The print line looks like a shrunk down version of the filament itself. So why the hell would anyone want to print with thermoplastic cowtails? First off, fiber-filled filaments are stiffer, and stiffening anything makes it brittle. But because you're sort of squishing this bullseye structure, it forms alternating layers of stiff composite and pliant polymer, which resist tension and compression like rebar and concrete. But also, fibers kill your printer. You already know that they will kill your nozzle, but remember the filament attacks everything it rubs against. If you print a lot of composites, you might want to check your drive gears, MMU assist, even the guide tubes. Everywhere filament touches printer has probably taken a substantial amount of damage. If wear and tear need to be minimized, AE Coating's outer layer puts a protective buffer between the printer and the abrasive filler. It also lightens the load on the drive gear because smooth filament is easier to pull through the filament path than rough filament. There's also an ABS version, which I don't have, but it's probably good stuff. How would I know? Well, I do have Siraya Fibreheart ABS GF. This is ABS with 10% fiberglass, and while I showed carbon-filled ABS in the very first episode, I could not find a supplier of its silicon-based counterpart. So this one is a previously industrial exclusive filament that only recently hit the mass market. ABS is super tough, but it loves to warp, and fiberglass does such a good job of reducing tachification, it basically neutralizes that weakness. At only 30 bucks a kilo, this stuff is a suspiciously cheap high-performance option. Here's another industrial staple that's becoming increasingly available to weekend warriors. Polymaker PC PBT. Alloys of polycarbonate and polybutylene terephthalate really are everywhere in industry. Junction boxes, light fixtures, mechanical parts, like everywhere. PC-PBT just has this great balance of impact resistance, heat resistance, and dimensional stability. And unlike most other thermoplastics, it doesn't turn brittle at sub-zero temperatures. But in filament form, PC-PBT is almost unheard of. Only a handful of companies make it, and only Polymaker seems to distribute it. But that is a shame. PC-PBT is an awesome multi-purpose material that's easy to print but hard to damage. I think the PC part spooks people because polycarbonate's straight up obnoxious. Polycarbonate. All my homies hate polycarbonate. Of course, when I tried to get footage of this, I got the only flawless polycarbonate print that's ever been made. Fuck me, right? But the blend prints nothing like polycarbonate. It's like more like ABS. If you are only going to try a single filament from this episode at home, make it PC-PBT. But enough Bush League bullshit. Let's get back to business with Nanovia. I featured this French firm's Teflon-infused polycarbonate in the Cursed Filaments episode. That articulated benchy was revolting. One of Nanovia's reps saw that print-in-place travesty and sent an overflowing care package packed with their exotic composites. They even included some fascinating custom blends special ordered by their clients, like this glass-filled TPU. The print isn't the prettiest, but man, this stuff is super strong. Oh, Zach's a hypocrite. He was bullying CF-TPU, but GF-TPU is good because he's got to slob the corporate knob. Well, yeah, I am an absolute hypocrite. I never really claimed otherwise. But look, GF-TPU is better than CF-TPU. Fiberglass stiffens filament more effectively than carbon fiber, and Nanovia was not stingy with it. This boat flexes so little, I am worried I'll snap it by trying. Does this sound flexible to you? Molten GF-TPU flows from the nozzle like peanut butter, so it's as obnoxious to manufacture as it is to print. Nanovia only sells this made to order in bulk, and mostly to medical device manufacturers who can afford to buy out entire production runs. Speaking of, here's Nanovia's PLA VX and Flex VX. One of the very first filaments I featured was an antibacterial PLA, and these are the big boy versions, polymers stuffed with nanoscopic copper and silver catalysts that annihilate microbes on contact. Bacteria are blimps compared to teeny-weeny virus particles, which makes virucidal filaments much more challenging to make. But those Frenchmen figured it out and made a formula that nails fungi, protozoa, and all manner of single-celled flora and fauna. And bonus, this reel of Nanovia Flex VX is actually a remnant of a special order run with way more of the virucidal additives than usual. The end product would be immersed in seawater, and the client wanted a flexible filament that algae couldn't grow on. The standard formula's primary applications are making sterile gaskets, manifolds, and sockets for medical equipment, hence the hospital scrubs teal color. Next is Nanovia Istroflex, one of the weirdest fucking filaments ever put into a 3D printer. It's got this pebbly, grippy finish and is fairly flexible at 93 short A. It's like average for TPU. But Istroflex is not TPU, it's TPC, thermoplastic copolyester. And it could be the only completely biodegradable flexible filament. Not like industrial composter bullshit biodegradable, like buried in the garden biodegradable. The secret ingredient is oysters. I kind of bury the lead on this one. This filament is full of oysters. Istroflex's satiny texture, beige color, and rapid decomposition come from a significant amount of ground up cosmetics grade oyster dust. Which cosmetics actually use oyster dust? I asked my wife Brooke, a licensed esthetician with over 2 decades of makeup artist experience. She didn't have a fucking clue. Nanovia presents ABS AF. Acrylonitrile butadiene styrene is boy! I'm just kidding. It's ABS reinforced with Aramid fibers, brand name Kevlar. Like carbon and glass fibers, Aramid stabilizes the polymer as it cools, containing the stinky plastic's notorious bending. But unlike carbon and glass, Aramid fibers are flexible, so they don't roughen the print surface, they don't need a special nozzle, and they don't make the print brittle. This is some seriously tough stuff. I printed an Aramid nylon benchy about a year ago. Right? Oh shit, that's this episode. Sidebar! Fillamentum presents Nylon AF80 Aramid, a nylon 12 filament with 8% Kevlar-style Aramid fibers. And by the time your print's done printing, the Aramid is no longer fibers. Nylon melts about 250-260 Celsius, and Aramid melts about 250-260 Celsius. So they just melt into an alloy without any of the reinforcing properties of Aramid fibers. They're not fibers, they're liquid. Fillamentum claims you can print this stuff as low as 235 Celsius, but get the out of here. Zach from the future here. Turns out Fillamentum AF80 Aramid really does print perfectly at 235 Celsius. Probably should have seen this coming, considering in a past episode we covered Tolman 230, a form of nylon that prints at only 230 Celsius, so I stand corrected. You fucking suck past me, you know-nothing piece of shit. Next up, Nanovia PETG ESD. This polyester is very slightly electrically conductive, so it dissipates static that would otherwise build up and fry the circuits within. This is a common property on what's usually a commodity product, but as you can see, there's something very different about Nanovia's version. If you can't see because you're only listening, or you can't see because you lost your eyes in a sword fighting accident, this filament is white. Almost all anti-static filaments get their properties from a conductive pigment called carbon black. This stuff is really black, especially at levels high enough to actually affect the filament's electrical resistance. Normally, black is fine. It is the color of tactical operators, ninja warriors, and serious fucking business. But in, say, a clean room where a single speck of dust can trash a whole run, you want every surface to be bright white so contaminants have nowhere to hide. So Nanovia swapped the carbon pigment for conductive ceramic, creating a one-of-a-kind icy white polyester that mitigates static almost as effectively. The exact compound is proprietary, but the MSDS says fiberglass, so I'm guessing they sputtered the glass fibers with an electroceramic like indium tin oxide. Pure speculation, I truly have no idea. But what's really mysterious is Nanovia's RFBlock PLA, a filament that attenuates radio waves. I was not given any information about this one, and there is nothing to read online. It could be meant to isolate sensitive instrumentation from interference. It might prevent high security tech from literally leaking information. Either way, there is some kind of conductive and/or permissive additive parentheses S that makes this filament act like a printable Faraday cage. Who commissioned it, what they did with it, and how the hell it's white when it really should be full of metal flakes will be forever locked in a dusty French filing cabinet. But Nanovia, ironically, gives us full transparency into their X-ray blocking filament, PLA XRS. The cool part is that it does this without exposing users to heavy metals. You wait your turn, Josef Prusameters of Prusament Prusa. The pigment here is barium sulfate, a substance so benign you literally drink a cup of it when you get a contrast X-ray. BASO4 is not as radio opaque as tungsten, but that's not necessarily a bad thing. It lets engineers modulate the strength of the shielding by varying the print's thickness. Put some thickness in your sickness. The final filament from this firm I feel like featuring is Nanovia SiC. I am sorry for spending so long in this one company, they just sent me a lot of cool shit. This is a sintering filament made of tiny fragments of a normally unprintable material suspended in an easily printable binder. You run a sintering filament as usual, you pack the so-called green print in a special sand, and you fire it in a furnace. The heat burns away the polymer and melts the powder particles into a mostly solid chunk of, in this case, ceramic. Don't worry about the complete failure to bridge here. When you're using a sintering filament, you design the geometry around the material's constraints like I did here. In the last episode, we mentioned BASF Ultrafuse, a metal sintering filament that I couldn't show you because the sample a viewer sent me got lost in transit. Well, Matter hackers pulled through, and here is what a raw Ultrafuse benchy actually looks like. This product includes processing, so you can send the green parts back to BASF, they'll debind, sinter, and ship you back the finished metal part. I haven't done this because they only give you one processing ticket per reel, so I have to finish the entire spool before I can cash my chip. But Nanovia SiC does not let your Ender 3 print metal. It lets your Ender 3 print the same ceramic you put in a plate carrier. SiC stands for silicon carbide, aka carborundum, an ultra-hard crystal that forms unbelievably tough ceramics, and its sintering temperature is a scotch higher than 2000 degrees Celsius. To put this in perspective, this Inox 316L stainless steel Ultrafuse sinters at about 2000 degrees Fahrenheit. I don't know anyone who could possibly process this benchy. You can fire metal, glass, and other ceramics in a tabletop kiln. You can also try an induction forge. Silicon carbide is a semiconductor, but you can't control that predictably enough to debind it first. The only thing capable of hitting the right temperatures to debind this, then getting hot enough to sinter it, is a high-tech piece of factory equipment called a vacuum furnace. According to Nanovia, this product's primary buyers are aerospace firms, and there actually are a number of those here in Colorado, and I'm I'm sure they can afford a vacuum furnace. So if you work for SpaceX and you're okay with an untrained amateur chucking a tiny boat of mystery material into Elon Musk's multi-million-dollar hotbox, hit me up. Nanovia also sent a few fancy super polymers. And so I can finally print them this time, Vision Miner loaned me their phenomenal 22 IDEX V3. This dual extruder monster has a massive oven for a build chamber, an airtight heated filament storage bin, and pretty much everything you need to preserve that persnickety peak. I can't afford movers qualified to actually get a skid-sized 200-pound, $15,000 3D printer into the workshop. We'll have to do that next time using the proceeds from these mid-roll ads. You just got mid-rolled. Now, Vision Miner's Fancy Pants IDEX printer might be imprisoned in my garage, but I did borrow another printer for the total opposite kind of filament. Not super tough, but super squishy. This is... well, it's complicated. Chemical megacorp DuPont contracted the Wisconsin-based Coex to turn their Hytrel resin into filament, and when DuPont discontinued their first-party products, the rights fell back to Coex. So this is CoexFlex, previously Hytrel. It's a line of polyester-based TPEs with superior chemical resistance that still stay soft below -50 Celsius. DuPont originally developed Hytrel for injection-molded gaskets and grips. It's available in an oddly wide range of hardnesses, from a rock-hard 80 Shore D to a wiggly jiggly 40. Guess which one I bought? 40 Shore D is really soft, and since Hytrel is compressible and elastic, the conventional shoestring-ass 1.75mm filament is basically unusable. To make the rope more pushable, many super flexible filaments are also sold in the larger 2.85mm gauge. But here's the rub. I don't have a 3mm printer. Nobody makes 3mm printers anymore. Almost nobody. This is the Lulzbot Mini 3, the company's first machine with clipper on board, and holy shit, this thing is a fucking tank. All the moving parts are on linear rails, and all the structural parts are steel or aluminum. Lulzbot still chambers their printers for 3mm by default, and they pick the LGX Ace Mosquito extruder. This thing has a super short filament path and a very grippy drive system that make it perfect for flexibles. So armed with the right gear, printing Hytrel was a cinch even at high speed. I really like this stuff. It's got a grippy high friction surface and a rubbery pliability that are very useful for projects and quite rare in 3D printing. You're gonna see the Lulzbot Mini a lot more in the next episode because we're gonna feature a bunch of rare and forgotten filaments. 3mm was the standard in the early days of prosumer printers, and you wouldn't believe how many experimental formulas crashed and burned years before 1.75mm took over. So hit subscribe. There are over 100 filaments left after this episode, like this polypropylene peppered with hollow glass nanospheres. We'll do that next time. Not a business filament. I don't even know who this filament's for. But while we still got PP on our lips, let's bang out a few professional polypropylenes. All PP is a pain in the ass. Its awkward semi-softness and tendency to curl are just more than amateurs can comfortably take. But a good PP is rugged, powerful, and cheap, so industrial users bend over backwards to jump on it. Regular old polypropylene is already the lowest density printable polymer. It also has perfect layer adhesion and insane tear resistance, so even single line Vosmode prints are indestructible and watertight. But number can always go up, or down, depending on which is more impressive. Michigan-based 3DX Tech specializes in high-performance industrial filaments, and Hyperlite is one of their most unique, a polypropylene alloy less than 0.9 grams per cubic centimeter. That's 25% less dense than PLA, and the only way to make a print lighter is by using one of those foaming lightweight filaments from last time. And you can actually fluff the PP. It's just done in another business. This is Convena by Infinite Material Solutions, and it's a hybrid of polypropylene and water-soluble PVA. By melding a water-soluble phase with co-continuous microporous morphology, Convena PP exhibits highly uniform pore size that should get Infinite Material Solutions copywriter thrown out a window. The filament is half polypropylene and it's half glue stick. You print the filament, you soak it in warm water, and the PVA dissolves. What you're left with is an ultralight polypropylene foam riddled with microscopic holes. And these are some quality holes, perfect for catching microscopic particles. Drag a shape into your slicer, disable top and bottom layers, switch to gyroid infill, and you have yourself a high turbulence, high surface area filter of custom dimensions that would be impossible to manufacture any other way. It's the same technology as those sketchy Kai-Parthi Porolay filaments from previous episodes, but PP's water resistance resistance just stands up better in moist environments. But every PP has a big drawback that blocks it from getting enough action. You can't support PP. Most PP is on the soft side, and it squirts out so sticky and gloopy it won't stay up long enough to bridge more than a couple millimeters. Normally, you just erect supports, but the instant PP touches PP, they are bonded forever, with one exception. Smart Materials 3D, yes, the carbon fiber TPU people, humbly present an actually smart material with an incredibly stupid name. InnovateFill PP support is specifically made to keep your sagging PP standing proud. This stiff white filament is itself mostly polypropylene, except special additives keep it from fully fusing with other PPs. Now, you just grab the top PP, give it a firm yank, and rip it right off the support, exposing a smooth, clean undercarriage. PP support lets you whip out your PP in previously impossible positions and take your PP places it's never been. You obviously need a multi-material printer, but I would only run this in an IDEX or tool changer. AMS-style filament changers are just going to bend your PP out of shape. And yes, I am demonstrating this with a banana boat benchy, no particular reason. While we're on Smart Materials 3D, I want to show you one final filament from them, the low-key fascinating PETG MDT. I almost missed this one, but an automated production line would not, because MDT means magnetically detectable thermoplastic. This polyester is imbued with superfine black iron oxide, ferrite, and it's highly magnetically permeable. This means when you expose PETG MDT to a magnetic field, it instantly and momentarily becomes a magnet. Remember the IGUS P151? This is the same idea, except using an inductive magnetic sensor. Very few materials behave this way, meaning you can detect MDT buried in almost any substance, including metals. Black iron oxide is non-toxic and non-reactive, so this is safe for food and drug production. And if purity is critical, those little ferrite flakes are so fine, the right sensor can even detect microscopic dust. But if you really need to see your model through anything, or make sure nothing can see through your model, the time has finally come for Prusament PETG Tungsten, brought to you by Josef. Stop calling me Josef Prusa of Prusa Research, home of Prusament by Josef Prusa of Prusa Research, home of Prusament by Josef Prusa. By volume, this is mostly PETG with a little bit of tungsten sprinkled in. But by weight, this filament is 75% heavy metal! Tungsten is dense. Tungsten is ridiculously dense. You think lead is dense? Tungsten is 70% denser. This is a 1 kilo spool with barely 100 meters of filament on it. This baby can fit so fucking little Prusament. I really should have weighed the benchy before I wrote the script, but this benchy's mass is
text-to-speech server error.
This thing is so heavy it feels unrealistic. My immersion is shattered. I'm acutely aware I'm making bad puns for money. Why would Josef, everyone's a maker but only I'm a Prusa, do this? Probably because he could. Ostensibly because X-rays and gamma rays will zoop right through conventional polymers like a metaphor through a half-listening viewer. Carbon, hydrogen, and oxygen atoms are not very big. They don't present a lot of surface area for EM waves to smack into. But tungsten is a basement dweller of the periodic table. And if you're a high-frequency EM wave, element W looks like the broadside of a barn. Tungsten filament is great at blocking X-rays, which lets any printer make apertures, markers, and filters for medical imaging, scientific instruments, and confusing the hell out of my dentist. But tungsten is so good at stopping photons. This Prusament can even block ionizing gamma rays. A wall merely 1.4 millimeters thick will slash incoming gamma radiation by half. You wouldn't even know my mail order Amazon uranium was in here. I also want to point out my radiation meter looks exactly like the EMF ghost detector from the ghost hunting episode, which confirms my hypothesis that the entire EMF meter exists to unload excess dosimeter parts on wackadoodles who believe in ghosts. Prusa's such a hobbyist household name, it's easy to forget how many of their products are designed for industrial use. After all, the company uses its own products to manufacture its own products. Case in point, Prusament PA11 CF. Nylon 11 is a polyamide like the more common PA6 and 12, but it differs by being a bioplastic. It's exclusively derived from castor beans by the French chemical conglomerate Arkema. As far as I know, only Prusament sells PA11 in printable form, and I think that's a shame. PA11 is more sustainable and more broadly useful than standard nylon. It holds strong at 150 Celsius, it doesn't deform under heavy loads, and it resists lots of useful chemicals. But PA11's real strength is not its strength, it's how easy the stuff is to print. Most nylon warps like crazy and gets waterlogged within hours, but when reinforced with carbon fiber, PA11 prints and stores more like ABS. It is the only nylon I have ever tested that would let me make a perfect print on the first try. I'll be honest, I almost skipped this reel because I thought it was just regular nylon with a fancy name. The same went for Prusament PETG V0. Buried beneath that bland branding is a unique fireproof PETG concocted specifically for industrial users. Standard PETG is common for electronics enclosures because it can handle 60 Celsius, the maximum operating temperature of many chips. The problem is PETG is flammable and it erupts into a nasty, filthy smoke. So Prusament modified this PETG to puff into an inert carbon foam when it catches fire, which smothers the surrounding plastic and keeps a fire from spreading. Flame retardant filaments are not rare. See, I can say retardant, it was a joke. But according to Prusa research, V0 is the only PETG filament that's UL certified self-extinguishing. The trade-off is a premium price and weaker prints. Can you believe Josef Prusa came up with all this stuff himself? It's just him and this factory with like 1,000 printers. While we're in Europe, let's check out 3D4 Makers, a terribly named Dutch manufacturer, utterly unknown here in America. They have a neat suite of unique practical filaments like this recycled peak. What the f was it recycled from? Tanks? But I want you to see their Facilan Ortho, a filament specifically designed for the business of the human body. Facilan Ortho prints at only 130 Celsius. So chilly you need to manually tweak the G-code to keep the printer from aborting the job to save you from yourself. It's one of those filaments that only sticks to some wacky bed treatment. This time, it's a full sheet label for laser printers. The things I do for like, comments, and Patreon donations. It also prints at an excruciatingly slow 10 millimeters per second with a minimum 60-second print time per layer. Ugh. What you get is a springy print with a waxy gloss, and here's the fun part. You dunk it in hot water and you can reshape it by hand. This lets an orthopedist sculpt a back brace, shoe insert, or prosthetic socket right against the user's body. No obnoxious 3D scanning, no scorching hot air guns, just a perfect fit. Practitioners can even adjust their work as their patients grow and develop, so the patients don't have to keep buying fresh orthotics over and over again. Facilan Ortho is based on polycaprolactone, an obsolete filament with a very low melting point. Pure PCl is borderline unprintable, but this modernized formula hardens faster and shrinks less. This makes it easier to print and reshape, plus it lets it bond to fabric, so you can craft custom insoles, soft braces, and resistance wear for physical therapy. Facilan Ortho inspires entire categories of new projects, and it opens up innovative new options for patients who aren't satisfied with conventional handmade orthotics. Our final business filaments are solutions looking for problems, incredibly rare, bleeding edge, and profoundly expensive. It's my privilege to even see these outside a research paper. We're going to start with another heat-sensitive filament, one of the rarest reels in my Raiders of the Lost Ark-esque filament archive, Convena SMP55 shape memory polymer. This slick translucent filament looks a bit like PLA, but when you bend it, it creases, not cracks. That's a lot of damage. The magic happens when I dunk the damaged print in hot water. It unfolds on its own and snaps back to its original shape. As the molten filament cooled, it wasn't just solidifying. Its geometry was being encoded into its very molecules. When I bent this thing out of shape, I was actually stretching the molecules like tiny bungee cords. When I softened the polymer in hot water, that tension dragged each molecule back into position, effectively reversing the damage. I am using a flimsy two-dimensional cookie cutter benchy to emphasize the effect. This does work with 3D geometry. The 3D model just has too much detail and thus too thick walls to get a good squish going. Applications actually exist. They include robotic grabbers, laparoscopic surgical tools, and airfoils. Surfaces you want to predictably reset to a known position, but can't fit in any motors or solenoids. You would run a heating wire around or even through the shape memory polymer, and you can trigger the effect electronically on demand. Just be aware this 100-meter sample spool cost over €200, and I had to get it through a Japanese manufacturer, through a German broker, via an American importer. But I did find a full reel of so-called SMP4D for just $20 a kilo on Amazon. That's even cheaper than PLA and extremely suspicious. It's called SMP4D because this tech is sometimes called four-dimensional printing, because you can like program a 3D shape to change over time. Obviously 4D is better than 3D. Number go up, always good. Unfortunately, I could not actually get the cheap stuff to work. And while the company provides demo STLs, those stupid motherfuckers set the Google Drive that's hosting them to full public permissions. So some random internet asshole deleted the test models. Everybody. Our next hemorrhaging edge material is also on the heat-sensitive pain train, though probably not by design. This is Multi3D's Electrifi, the most electrically conductive filament by, at least according to its North Carolina manufacturer, a factor of 100. Saturated with nanoscale copper shards, this stuff's nominal resistance is a mere 6 microohms per cubic centimeter. The product page claims if a circuit can handle 10 ohms of impedance, you can print that circuit in Electrifi. That is a huge spread of projects and prototypes. By combining Electrifi with conventional filament, you can even print capacitors, inductors, and antennas. One of Multi3D's demos is a fully printed wireless power receiver. But should you? For one, this filament is over $1,700 a kilo, and you need thick traces. It's not that conductive. Fused filament fabrication is also an inherently clunky process, and a 3D printed circuit board looks like caveman technology. But worst of all, Electrifi melts at only 130 Celsius, about 100 degrees below standard filament. I cannot comprehend what possessed these people to make their filament polycaprolactone. I am genuinely afraid to ask them, because anyone who makes filament out of polycaprolactone for no reason is fucking psychotic. In an AMS-style material changer, it runs too cold to ram the other filament out of the nozzle. Multi3D's demo footage shows a custom extruder with dual tandem auto-lift self-retracting hot ends. A really funky setup I have never seen before. Oh, you also can't solder it. Components and wires have to be screwed down, glued with conductive adhesive, or reflowed on your printer's heated bed. Like a reflow oven, except the entire circuit board is made of solder paste. What could go wrong? Electrifi filament actually has one very rare and potentially useful property. It's bendable. To explain this, let's see another flexible conductive filament that does not have this property. Recrius Conductive Filaflex. This carbon black TPU has a much higher resistance. It's like a few hundred ohms per centimeter. It's just TPU, so we could actually print this onto fabric like the t-shirt My Cursed Printing Tricks episode to make washable wearable circuits. Kind of f***ed up, but also pretty cool. But I only need a little strip to make my point. The more I bend it, the lower its resistance. When I bend the print, I'm compressing the TPU, which forces the conductive particles closer together so they make greater electrical contact. We can actually harness this by measuring the resistance, and voila, we now have a custom printed bend sensor. Unfortunately, we can't really use this for circuits because its resistance is going to be changing all over the place. While Electrifi is also flexible, it does so by bending, not stretching or squashing. There isn't as much tension and compression mashing those metal flakes together, so Electrifi can flex without substantially changing its electrical resistance. This is a very rare property, and Multi3D used it to make a fully flexible 3D printed lithium-ion battery. Maybe one day I can get some of that custom lithium perchlorate filament they concocted for that experiment. Call me. Our final filaments are the deepest of deep cuts. Ultra niche, ultra esoteric, and ultra expensive. These are nanotech composites from Colfeed 4 Print, a Spanish firm that makes super specialized filaments for scientific research. These samples are among the rarest, most exotic filaments ever sold, and almost certainly the most expensive. While seeking out new filaments to test, I ran into a research paper by a team of PhD material scientists in Madrid. They were working with wild experimental composites unlike anything I'd even heard of, so I reached out to the authors, hoping someone could hook me up with the leftovers. To my surprise, I got a response. The authors had left and their labs were gone, but not because they gave up, because they went into business. Their new company, Colfeed 4 Print, has a whole portfolio of exotic research-grade composite filaments with incredible properties. I would be the very first American media outlet, not just YouTube channel, to feature them. I'm kind of a big deal. Full disclosure, I could not successfully print these filaments. They were too brittle to unwind from the spool, and they were so fragile, the drive gears of all my printers crushed them to powder, even at minimum tension. I tried all my printers, I tried minimum tension, I tried heating things, I tried everything. These are over 50% solids by volume, and they need a filament warmer and spacing adjustable extruder gears to run things properly. I learned this too late and wasted too much filament. So these printed models are stand-ins, which I carefully match for color, texture, and presumably mouthfeel. Thankfully, Colfeed sent some pre-printed samples, so you will still get to see the real deal. Our first Colfeed for print filament is a carbon fiber PLA, the way a bottle of vintage Dom Perignon is Bunch of rotten grapes. This is Filament Eco CMO3 infused with Timurex SFG44 synthetic graphite with particle sizes consistent within the tens of microns and uniformly dispersed via a proprietary colloidal process. FECO CMO3 lets researchers fabricate custom electrodes with precisely tailored properties to use as is or to electroplate with a relevant metal like platinum. And you will need a research grant to buy this. Colfeed sells this 10-meter sample of FECO CMO3 for €160, which comes out to just over $5,000 per kilo. That means dollars for donuts. This is the most expensive 3D filament I have ever seen. But hot on its heels comes Colfeed's Filament Ser ZR02, a sintering filament that, with the right kiln to debind and fuse, allows you to print 3 mole % yttria stabilized zirconium dioxide, which you've probably mistakenly called cubic zirconium. Zirconia is a hard, tough, and fracture-resistant ceramic with excellent chemical resistance used in dentistry, high-temperature production processes, and jet turbines. It shields metal blades from heat that really should melt it. It's a common substrate for catalysts, sensors, and electrochemistry like fuel cells. Unfortunately, the processed zirconia does not look like a big sparkly gemstone. It looks basically the same, just a little bit smaller. Remember, this has been sintered. It's not one monolithic gemstone, it's bazillions of microscopic grains partially welded together. This is by design. The more surface area the print has, the more real estate you get to attach, capture, and impregnate with other substances. If you really feel like printing lab-grade pure harder than rock zirconia, you'll need to shell out €330 per 10 meters, or about 4,800 clams a kilo. It costs less per kilo because it's about twice as dense as the carbon fiber. Today's final filament is, frankly, the coolest, most futuristic thing I have ever put on this channel. And that includes the wearable computer I'm using right now. This is Colfeed 4Print's Filament OS Has-Int, a sintering filament that processes into 100% pure medical-grade hydroxyapatite. In the Cursed Filaments episode, I presented 3DX Tech SimuBone, a filament with many of the properties of real bone, but not capable of being implanted like it. This filament does not share that weakness. FOSS Has-Int lets you print authentic, biocompatible human bone. When you implant hydroxyapatite in bone tissue, that's the spongy inner part, it acts like a scaffold. The cells start forming hard bone in and around the synthetic material and even run blood vessels to supply it. Over time, your body absorbs the synthetic implant and replaces it with natural bone. FOSS-HA lets orthopedic surgeons print bone scaffolds specifically tailored to the patient's exact physiology, so they can help heal birth defects, recover from cancer or physical trauma, and even help implants fuse directly into the bone itself. Who knows, maybe when you're a dried up old fart muttering about the good old days when eggs were only $9, your femur will be filament. This stuff costs a whopping €240 per 10 meters, or about 4,500 freedom tickets per kilo. So marked up by health insurance adjusted for inflation, estimated profit margin in America with 35 straight years of completely unregulated oligarchy, you're gonna spend your retirement cracking rocks in debtor's prison, but at least your hip will work. No one will be able to call you unhip. And that is my collection of filaments that are literally reshaping the business world, unlocking revolutionary new horizons in the art of next-gen dead-end R&D gold breaking. For no matter how high the price of innovation, if you can write it off, it's basically free. If you found a filament I haven't featured, let me know by pinging me on discord.gg/voidstarlab or email me at partnerships@voidstarlab.com. Not every filament is unique enough to feature, so I can't promise it'll make it on, but I can't know till I try it out. I'd like to thank the many companies and reps who gave me access to pricey and or privileged products. Down in the description, I've linked every filament I featured, or the company itself if a direct link is unavailable. Hell, the companies I'm mentioning may have gone out of business last year, and I'm only finding out now because I took a year to make this episode. Can you cut, please? But our patrons deserve a whole other dimension of thanks. Even with all the corporate freebies, I still had to spend thousands of dollars hunting down rare, exotic, and experimental filaments. Your support doesn't just fund this work, it frees me up from having to crank out content slop to farm ad revenue so I can feature filaments that take entire days to figure out. I'd like to give you at least 3 more every filament episodes, so if you'd like to support that, visit patreon.com/ZachFriedman. Who knows, I may even end up reading your silly username, like our 3 featured lab scientists, the Pink, Mark the K, and Forklift Certified. Our generous Maximus collaborators Our ZomboDB, GridFi.cc, the Suits Ruined Our Fun, Schleppy the Schwagster, Chuck Me Harder Baby, Turner's A, SXP, Microwave, the Benevolent Misanthrope, Scott Rainey, and introducing Zachary Vulpes. I've hidden their names in one or more Easter eggs, and you've seen their plaques plastered all over the printer. Your name could be there too, just saying. This video is so friggin' long, I am not worried about YouTube punishing me for reading our lab assistant's humorously long names in full. So buckle up, Buttercup. Give it up for Cameron Ogletree, Comrade Spamuel, Reagan, Zach with a CH, Scroto Saggins, Tevin, a unicorn, or maybe an alicorn. Trans Rights, Bill Moore, T. Moore, Aaron Steers, DBD, Stardelos, Brad Cox, Cliff Henning, Dennis Kempin, Tactical Possum, Doom Crew Inc., Acalia makes Zach say trans rights are human rights. I'll say it again, trans rights are human rights. Kathy and Brent Irvine, Danny Devoid of Life, Spire, Blammo, Protagonist, John Zobrist, Rusty Flute, Bill Schooler, Al Finger, Zach Harvey, Ergay, The Monk, Antitux, probably not 3 raccoons in a trench coat, Crash Doom, Nuclear 314, King Shaming Walrus, Burundock 3, Renaud Bataille, Paul Gibbs, El Presidente, Daniel Morgan, Roger Pinkham of the Great Star Theater, T.R. Fullheart, Powerful CCH, William Tancredi, DVM, Rihanna 99 and Urch, Sarah Clancy, even Bluetooth has a right to repair, Amanishi, Partial Eclipse, a sharp pucker up, Brown Eyes, Good Suck, Grurg, it's supposed to say Grurg, well thanks for clerking that up. No Disassemble, Gotham Vermichenny, the haunted leaky water heater upstairs, I pay good money and Zach didn't read this. Or did I? Also, you spelled my name wrong. VK2KTJ, Agent Maxwell, Eddie, Good Lady Nat, Queen of Lemons, Victor of the Great Citrus Wars. Dr. Mrs. the Mirrorman, Mirrors and Mere Mortals, not Merman. Land Jesus will die for your sins. R. McKeel Ralston, Nova Ren, Cody, Wuhan Express, Deny, Defend, Depose, My Printer Broke Again, Craft Computing, John Loves Jen, The Q01, Big Bird Tommy, What Goes Bump in the Night, Travis Hippa, Moonkin, Haley Kerman, Cullen.zip on Blue Sky, Callsign Carrot, Viwatch, Stormy Design, Acorn, Lydia K, The Snow Chow Cabal, Chows in Chaos equals Cow, Cameron McPherson, Jeffrey Haas, Period Clots, T-Kites, Take It Easy, Igor Box, Shane Frederick, Chris Floofy, Kitsune, Travis Pocky, Michael, Clayton Easley, not Prince Michael of Sealand, Robo Chemo, Robert Breeze, The Curlster, Quantumly Tingled, Max Luck just woke up for a 3-month coma, Max got hit by a bus and lived. A 3rd time? You should wear a helmet. Slippy McToof, Kevin DeGraff, SKL, Robert Cox, Alex Perrin, Joseph Ribka, Iron Rain, Dan Ryan, PRD, Mike Kelly, Sticks Like the River Not the Band, RTB, Dale Bibi, Zap Sunburnt Cat, Evanosaurus Rex Kinney, 6A, 6F, 65, 6E75, Michael Creamer Jr., Talon Democratic Socialist, and a pretty righteous dude. I think I changed my name to Lost Dryer Socks, Bryn 6 Foot 5 Figure Forlorn, Wolf Schulte, Quality Doggo, Zenforian, D-Orbital Mechanic, Des Baldonado, Tony Guntharp, Kermit the OG Frog, Onyx Plague, Sox McGox, Bob Dobbington, Jack Moran, and Martin Titonium! Thanks for watching, and it's in the script.